Hello and a good day, everyone. Today, my group and I are here to talk about our group assignment 2 for maths, ENG 3002, and we are from group 4. And first of all, I would like to introduce myself. My name is Kitash Ankisasalam, and my metric number is 211948.
Hello, my name is Mognesh Yogeshwaran and my metric number is 213018.
Kevin.
Hello everyone, my name is Kevin Santana Anthony and my matrix number is 211491.
Hi everyone, my name is Muhammad Zafiq bin Muhammad Zahan Pang and my matrix number is 192006.
Thank you everyone for your introduction, and I would like to now continue with our assignment. And I want to just mention that our title of this assignment is the application of sonar system in underwater using wave equation. So I'll give the introduction will be done by Kevin now. Okay, thank you.
Okay, thank you, Kirtiraj. Okay, first of all, I'll be explaining about sonar and radar. A boat or ship must gather data about its location and surrounding, such as potential obstructions, topography, in order to travel safely. So radar devices have been very helpful for ground and aerial vehicles, as we all know. Due to electrical conductivity of salt water, radio waves are electromagnetic radiation that are often damped to dissipate after 1.5 wavelengths. So in order to meet the problem of underwater range, sonar systems have been created. So what is a sonar? That's the question here. So sonar system can be active by transmitting and receiving, or passive, which means just receiving. So the majority are active systems. So sonar typically have a control unit, a transmitter, a transducer, and a receiver. The transducer transforms electrical energy to acoustic energy and vice versa. At specific frequencies, transmitter produces an oscillating electric field. The receiver boosts the electric signal and transforms the analog signal into data that can be processed. Data processing will be handled by the control unit. So that's all about the sonar, this sonar system. And after this, I'll be explaining about I'll just explain simply about the wave equation. So it's actually the displacement of wave propagation of sonar is proven to have wave equation by the solution, which is 1 over v square delta square y over delta t square, which is the second partial derivatives respect to t, equals to delta square y over delta x square, which is the second partial derivatives respect to x. And the propagation wave speed used in the ultrasonic wave is given by a solution of this equation where v equals to omega over k. So yeah, that's what about wave equation. So that's all from me.
Thank you, Kevin. So now the engineering problem will be explained by Mognesh.
Thank you, Kirtiraj and Kevin. Okay, I will talk about an example of engineering problem. Okay, sonar is installed in a boat or a ship. The transmitter transmits ultrasonic wave. These waves travel through water, and after striking the object on a seabed, the wave get reflected back and are sensed by the detector. The methodology used is wave equation, is a semiconductor partial differential equation describing standing wave field. So the equation is given by yxt equal to a sine kx minus omega t, where t is time in seconds and x is displacement on axis in meter, omega is angular frequency, s per second, and k is wave number. So the engineering problem is verify that the function satisfies the one-dimensional wave equation. Hence, sketch the graph of the solution y against x at t equal to 0 using the step size of x equal to 0.0005 and using different value of a. The amplitude which are 1, 3 and 5. So you need to use the given information to find the unknowns and solve the solution. So that's all from me.
Thank you, Moga. And now I would like to move on to the solution or the calculation for the solution. First of all, I will explain about how we find the unknowns we have to. In this case, before that, we have to prove that it's a wave equation. So in this case, we will use the y xt equals to a sine kx minus omega t. We have to partially differentiate it twice in respect to x and also t, and we result it with y xx is equals to negative ak square sine kx minus omega t, and for y tt, which is the second partial differentiative of respect to t, which is negative a omega square sine kx minus omega t. And then with this wave equation, we have a rule in which, based on our concept of sonar waves, we have the ratio of the acceleration and the curvature leads to the very important relationship in physics known as wave equation. So we divide the equation 2 over equation 1, taking the ratio and using the velocity equals to omega k yields the wave equation, in which we get the delta square y xt over delta x square equals to 1 over v square delta square y xt over delta t square, like the one Kevin said in the introduction. Clearly, these derivatives are one-dimensional wave equation, and it proves it's a wave equation. Okay, let's move on to finding the value of k and omega. Finding the value of k is the wave number, which is 2 pi over lambda. And we use before that we have to find the lambda. Lambda is the frequency. You can use the function, the equation v equals to f lambda, and we get the lambda value of 1.5 cm, and then you substitute the value and we get the wave number of 400 over 3 pi meter per negative 1. And finally, we get the angular frequency, where it's used with the formula 2 pi f, and you transfer the frequency. In this case, is 100,000 hertz, and we will get the value of 2 times 10 to the power of 5 pi seconds negative 1. And finally, we have the substituted equation with y for y xt is equals to a sine 400 over 3 pi x minus 200,000 pi t, where a equals to 135, which is the different amplitudes are used for the solutions. So now we find the values and shown in the table. We have 3 different tables for 3 different graphs. So as you can see in the graph, we have different amplitudes of different heights. So like the one with the yellow line has the one with the lowest amplitude, which is the 1, and the orange line represents with the amplitude 3, and the blue lines represent the amplitude of 5. So that's all from the calculation, and we move on to the conclusion. I hope everyone understands.
Okay, thank you, Kitiraj. So for the conclusion, as for the conclusion of our report, in the beginning, we have given an introduction on the sonar systems and its purpose. And so we can conclude that it is reliable in exploring and mapping the ocean, which have been used in many applications, especially maritime transportation. So due to sound waves travel farther in the water than radio waves, making this system to be more practical than radar devices. So after that, we have explained how wave equation has been used to model the sonar waves in data analysis, and how the equation y xt equals to a sine kx minus omega t is used to produce a wave propagation graph. So then the solution for the problem was shown step by step. Based on the problem, the function given was proven to satisfy one-dimensional wave equation by taking the partial derivative with respect to x and t, and by using these two equations as ratio, which yields wave equation. Then solution was found by finding the values for k and omega, and then substituting these values, we obtain an equation of y x t equals to a sine 400 over 3 pi x minus by 200,000 pi t. And then by taking the step size x equals to 0.0005 and t equals to 0, a sinusoidal graph was plotted describing the wave motion. So three different values of a were taken to make three different wave propagation graphs. The difference between these three curves is their highest peak, which were determined by the value of a. Then it can be seen that all three sinusoidal curves have similar wavelength. The value of the wavelength can also be obtained directly by dividing the speed of sound wave in water by the frequency. And therefore, to conclude, the solution found throughout this problem proves that a single wave propagation can be calculated by using a second-order partial differential equation. So that's for the conclusion.
Okay, thank you, Zafik, and thank you, everyone. So it seems that there's few mistakes that we fixed, but that's for the report now. And thank you, everyone, for the contribution. I think this is a good report, in my opinion. So I want to thank everyone for your efforts. So thank you, everyone. So that's for the video. Okay.
Okay, thank you so much for the cooperation. Thank you, guys.
Yeah,
Thank you.
thank you, everyone.
Uh, just before we end the video, I want to just share a few how I used my Excel to find the values. I plug in the equations for the x-axis and the y-axis. For the x-axis, we put in the value for the step size, and then the y-axis, I just put in the equation like the amplitude times the sine 2 pi, and then times the x minus 2 pi times 100,000 times t. And then I did it for a equals to 5, a equals to 3, a equals to 1. I know it's messy, but it's the way I did the graph. And then I finally got the values. And then you can see the graph as there's varies with the different amplitude, but the wavelength is the same nonetheless. And as the frequency and the wave speed is constant. And then we found the wave propagation graph based on the t equals to 0. So that's all, I guess. So that's what I want to just catch up with everyone about how I did then find the graph using Excel. So that's all for me. Thank you. Hello and a good day. I'm sorry I have to just extra record extra for these certain parts. I have to talk about the mistakes as course it has been done in the report. For instance, like uh, the certain parts in the report I have not fixed the original and the final values, such as like in this case, like not here actually in the solution. There are a few parts, if I'm not mistaken, like the equation 2 and 1. I think something's wrong with that. I forgot to talk to it. I also understand that from the conclusion also, I forgot to change the data. It seems that I forgot to use the A equals to 135 value. I also want to remind that the values I have obtained from the for this graph is not actually complete. I used an Excel to get the graph like this. So that's why I just wanted to just recap a few parts that I forgot to tell in the original part of the video. So just extend this video a bit. Just put this until 0.053 because it's not enough space to fill the whole word with the graph. And so I thought it's just do this, it will be much easier and be more clean. And that's all, I guess, for time being. And I have to see something else if there's others. For time being, it's okay. Maybe we have to reduce the introduction maybe here and there, but for time being, I think everyone's okay with it. Yes, I suppose. Yeah, I think maybe we have to reduce the introduction a little bit because it's too long, but it's okay, I think. I suppose everyone's okay with it. The reasoning is nice. Thank you. Values are correct, I think. But I think for the time being, this is a good report. But we can just leave it as it is. Thank you. Okay. If there's any more problems, I think we can discuss in the WhatsApp group, because we can fix it. And that's all the problems for the time being. Okay, thank you very much.